Let's talk about something called triangle inequality. So what is triangle inequality? From geometry, you know about this, right? If we have any triangle, then from triangle inequality, what we know that sum of any two sides will be bigger than the third side. Correct? The sum of any two sides will be bigger than the third side. So if I call this as vector A, if I call this as vector B, then the yellow line will represent the resultant of A and B. So we can call the third line as A plus B. The way of writing means A and B, right? So the third line is representing the resultant of A and B. Okay. Now, what triangle law says that the length of A and the length of B, if you add these two length, what to expect? This must be bigger than or equals to the length of the third side. Okay. And what else we know that the difference of two lengths, I need to put one more modulus y because I don't know which one is bigger. So the length of the difference of length of two sides is always less than or equals to the length of third side. And if we combine these two, what we can say? So this is called the triangle inequality. And that's logical. Okay. That's very intuitive from the Euclidean geometry. So when the equality will hold true, can you tell me about the equality, the equal sign? This is called inequality, which means it is equal to and not equals to both. So when the equality will hold true, when the vectors are collinear or parallel vectors. So for parallel vectors, it is possible that the triangle will convert into a line. So if A is like this, B is like this, then the resultant is going to be like this one. And so the length will be how much? The sum of the two lengths, right? So the length of this resultant will be simply the sum of length of A and length of B. So we can say the equality holds true when they are parallel. Okay. Or you can say unlike parallel, then the difference will be there. All right. So this is possible. Okay. So they may ask you questions like this. So if I give you three lengths, 5, 10, 20, are these representing a triangle? Yes or no? So you have to figure it out that are these triplets are part of some triangle? Yes or no? Okay. Tell me guys.
Sir, I think it won't be true.
Yeah, correct. It is not possible. So what is the simple test? Take any two number. Let's say I'm taking 5 and 10. Take the difference. The difference will be the least possible value is 5. So the difference is 5. And what is the maximum value? 15. So the sum of the two sides must be bigger than the third side. You can see 15 cannot be more than 20. Correct? Or you can say the remaining number does not lie between these two categories, which means it must not be a vector. It must not be a resultant of the vector. So this will never form a triangle. For triangle to form, if you choose any two number, the third number must lie between the sum and the difference of the first two number. Simple rule. Choose any number. Let's say if I choose 10 and 20 and 5, the sum is 25, the difference is 15. So any number between these 15 and 20, the third number should lie. So you can see the 20 is more than 15, which is correct, and 20 is less than 25. So these two, did I make some mistake? 25. Oh, so what is the number left? 10. So you can see 10, does it lie between 15 and 25? The 10 is less than 15, right? So it will never fall in the range of 15 and 25. So this is again not possible. You can choose any pair, it will be true. So you can choose, let's say 10 and 20. The sum is how much? 30. The difference is 10. And the number left is 5. Now again, 5 does not lie between 10 and 30. We can clearly say it must not be forming a triangle. So this is not going to be part of any triangle law. Okay. For triangle law, what is condition? The third number should be between the difference and sum of the first two number. That's it. So if I ask you 5, 5, 5, can we form a triangle?
Yes, sir.
Yes, sir.
Definitely,
Equilateral.
it's an equilateral triangle. In fact, we can see it. So if you do by the method, the sum, the 0 is the minimum and the maximum is 10. And the third number is of course between maximum and minimum. So it will form a triangle. So if I give you a number like 15, 10, and then 20, is it possible? So is it possible to have a triangle?
No, sir.
Why no?
So because 20 does not lie in the difference of 15 and 10.
No, difference and sum. Difference is the lower limit. Sum is the upper limit. It should be between lower and upper. So now,
Yeah,
Yes, sir. It is possible.
it's possible.
it's possible because because you can see if you take 15 and 10, the difference is 5. Sum is 25. Now our third number is 20, which exactly lies between these two numbers. So as long as it lies, it is possible. Now if I ask you, is it possible for this to represent or follow the triangle? Now you have to also believe that a flat triangle is also possible in vectors. Is this possible?
Yes, sir. It is
Yes,
possible.
sir. It is
Yeah. It is simply if you add these two, you will get 20. So 0 and 20, and 20 is at least equal to this value, which means the equality is holding true. So this is possible. These are parallel vectors. These are basically parallel vectors. So 10 and 10 are parallel, and so 20 is the resultant of the first. Okay. So these are again possible values. So the triangle inequality gives us the idea that whether a triplet, if I give you some random numbers, you can easily guess whether this number can generate a triangle or not. Okay, so the idea is whether it can generate a triangle or not, and if it can generate, it means it is following some triangle law. Okay. With the special case, the equality can also hold true. So equality is also a case taken in this case. Okay. A triangle with zero area is a straight line. You can think this way. A triangle with zero area means all lines are parallel to each other, right? So it doesn't form any area, but it still be considered in a vector. Okay, they are part of triangle law. All right, so this is a very simple concept, and we should be just aware of this. So apart from triangle law, do we have some other law in physics? The answer is yes, we do have. So what is the next law that we should be aware of?
Polygon.
So we do have a law called parallelogram law of vector addition, and what it says, if I want to put into the literature, what we can write. So it simply says that, let's say if we have two vectors, and what we are doing is we are taking these two vectors as the two adjacent sides of a parallelogram as the co-initial vector. So I'm taking these two as co-initial vector. So my vector A and my vector B are now co-initial. You can see co-initial. What is the next step? Complete the parallelogram by drawing two parallel lines. You can draw a line like this, and you can draw like this. Now you can name it. If you name it, if this is A, this will be also A. Why? Because when you translate a vector parallel to itself, it remains unchanged. That's a law. A vector moved parallel to itself will not affect. So A will remain A, and similarly we can say this as B. And therefore the resultant will be which vector? So if you draw the diagonal as a co-initial vector from the A and B, this will represent the resultant, and which we can again prove by the triangle law. So if you look at the lower triangle, what you can say? R equals to A plus B. What if you use the upper triangle? Can we say B plus A represents R? Can we say? So you can see R can be expressed in two ways, A plus B or B plus A, and both end up the same diagonal. So can we say from this triangle that A plus B is same as B plus A? This is called, we have discussed in the last lecture, we'll repeat one again. What we call this? Commutative law of vector addition. This is called commutative law of vector addition. Is this clear? So what is the commutative law? When you change the order of operation, the end result remains the same. We say such operation as commutative. Okay. So if you want, you can put into again literature. So vector addition follows commutative law, that is order of operation doesn't affect the end result. Okay. So I gave you the example that if you have shocks and the shoes, there is an order of wearing, right? You first take the shocks, then shoes. Can you alter the order? No, it will have a very different result. So similarly, in vector, the a plus b and b plus a having a meaning that they end up giving the same vector, and that's why it is commutative. And for your information, going into future, not all mathematical operation in vectors are commutative. We'll come to that. Not everything is commutative. So there are things which are non-commutative as well. But addition is always commutative, that is for sure. So here comes the idea. I told you that the finite angles are scalars, but elementary angles are vectors. Once again, finite angles are scalars and the elementary angles are vectors. Why and how? We will prove it. Finite angles do not follow commutative law of vector addition, whereas elementary angles follows. I will prove it practically. So you all will help me in proving this. So what I will do is, you can take a notebook, take your notebook in your hand, use your both hand, hold in front of you the notebook. Yes, hold in front of you, everyone. So what you will do is, let's say you're holding the notebook. Yes, very good. So about this axis, turn 90 degree. Turn 90 degree in front of you. Like this, front, in front of you. Turn in front of you, this way. This way. Yeah, correct, correct. Yes. So turn in front of you. So again, go back, the way it was. Turn 90 degree in front of you. 90, 90. Yes. Go 90 forward. Go 94. Yeah, that's correct. This is the first operation. You turn by 90 degree. Okay. The next step is turn this way by 90 degree. After the first event is done, turn this way 90 degree. Okay, like this. Now you can see. Now go back to the original position. Original. Yeah, original. Now repeat the steps in the reverse order. First turn like this. Yeah, in front of you. Yes. Keep the hand the same way. Just turn anti-clockwise. Hand anti-clockwise. And then in front of you. The plane should be the same. Yeah, turn like this. Raise the left hand and lower the right hand. Yeah, that's it. Exactly. That's the step 2, right? That's the step 2 actually. Now do the step 1. Move it, rotate forward. Rotate forward by 90 degrees. No, rotate forward. Forward. Yeah, forward. Go. Yeah, come this side. Come this side. Yes, correct. Now correct. Now what you can see, the book is having different orientation after 2 rotation. We change the order. Are we getting the same answer? Okay. So what you can do is, you can go back and repeat the step and realize after 2 rotation, the book is not in the similar fashion. The book is into the different orientation. Let's do it again. Yeah, go back to the original. Go back to original. Step 1 and step 2, and then reverse it and see the effect. Step 1, forward and front. Yes, raise your hand, left and right. Raise. Yeah, correct. Now this is the step 2. You can see this is the final orientation. Remember this orientation and go back. Go back to the original. Repeat the process in the reverse order. Repeat the process in the reverse order. Is it same? Now, this is called the order of operation. The book turning turns out to be giving two different results once you change the order. For sure, it is not following the commutative law, isn't it? So what we can say, since theta 1 vector plus theta 2 vector is not theta 2 vector plus theta 1 vector, which is against the very premise, which is against the very premise that vector addition must be commutative, which is against the very premise that vector addition must be commutative, and therefore they fell into the category of scalars. Okay, take your notebook and repeat the experiment, but now with a very small angle, just slightly turn d theta. You can choose a small value, doesn't matter. But take your notebook. Yeah, come once again. Okay, ready? Now turn slightly, not much, just a little bit. Step 1, forward turn, tilt forward, slightly, no, no, not much. A small value, slight, just slight, maybe 10 degree. Okay, and then turn anti-clockwise. Raise your hand slightly. Raise your left hand, but just that, enough. Now remember the orientation. Okay, now go back. Now do the repeat, reverse step. First turn anti-clockwise slightly, just, and then turn forward. Same. See, the book is in the same orientation. What is the magic? For a small angle, it is commutative. Very difficult to believe that elementary angles follows the commutative law. Big angles don't follow it. Okay, and that is the reason d theta 1 plus d theta 2 is actually equals to d theta 2 plus d theta 1. This experiment was first performed in the MIT way back in 80s, I mean 1800, I think. Okay, so the vector addition must be commutative, which is actually followed by the small angles, or you can say elementary angles, and that is why they are called vectors. So it is the biggest difference between the big angle and the small angle. So while going into the chapter of rotational dynamics, this idea will be very helpful to us. And what is that? That small angles are vector and big angles are scalars. Okay, and which is which can be proved by the commutative law. Okay, so after the, okay, and you can again use the parallelogram which you have drawn to get the angle and so on with it. So let me do it again. A vector, B vector. We complete the parallelogram. And the resultant is going to be like this. The angle between vector A and B, we can call this as theta, the way we used to assume. And this is the resultant. This is the alpha angle, if you remember. And now what we can do next is, now we can draw the perpendicular and complete our right angle triangle. And we know everything. So this is B sin theta. This is B cos theta lengthwise. This is lengthwise A. This is lengthwise V R. And again, you can do the same calculation as you did earlier. So R is equals to under root of A plus B cos theta whole square plus B sin theta whole square. So the resultant of two vector is the very famous formula A square plus B square plus 2AB cos theta. Okay. And we can also write the tan alpha again, the angle made by the resultant with the A vector, and tan alpha turns out to be B sin theta upon A plus B cos theta. So this we have done, but just we are repeating for the sake of writing. So we should always be aware that how to derive the formula from the simple trigonometry or simple geometry. The Pythagoras triangle is the, or the Pythagoras formula is the way to go ahead in the mathematics. Okay, that is the only law we know, and every other law we can derive from there. How? By drawing multiple right angle triangles. Okay. The third law that we should be aware of is called the Polygon Law, which is simply the extension of triangle law. And as we know that a triangle law or a parallelogram law works for two vectors. So what if we have three vectors, four vectors, five vectors, or 4,000 vectors, all in a same plane? Let's say we have a n vectors in a plane. So if we have n vectors, n coplanar vectors, and if kth vector starts from the k minus 1th vector, like you can choose some random vector, like third starts from the second, fourth from third, fifth from fourth, and so on. So if any vector starts from the tip of the from the then the line joining the tail of the first to the tip of the last gives the resultant vector. Okay. So, or you can say the line which closes the polygon gives the resultant taken in reverse order. So I will just make it change. So for example, if you watch football or hockey, you can see this event happening very comfortably. So in a game of football, we have something called pass. Okay. So let's say we have the corner. Let me make a corner. So we have a corner, and now what we have is a football. And then let me draw the goal post somewhere here. So you know that there are multiple players playing this game, and everyone will pass the football So let's say the first player kicks the football in this direction. The other player is standing there, and then he kicks next. Then the player will stop the football and will kick again. So the third player kicks like this. And then the fourth player kicks the football. The goalie is there, so he kicks to the nearest player, and looking at the other player sitting there, he kicks in the other direction. Then comes the Neymar or Ronaldo or whatever, like Messi, and then the final kicks goes inside. The goalie does nothing. Right? So you can see these lines are representing actually vectors. Okay? And the length of the line is like the displacement, how much ball gets displaced during every pass. So this is essentially a polygon, of course, not a nice polygon called the regular polygon. It's just a polygon because we have multiple sides. Now, what Polygon Law says that if you want to know the resultant, what you need to do is just draw the closing side. What is closing? The first click and the last. This is the polygon. It need not to be a nice polygon. It could be any random polygon. Okay, this is the Polygon Law. So what it says that the resultant is what? The beginning of the first and the tip of the last. So this will give you what? Resultant. And what we have vector, let's say A1 is the first vector, A2 is the second vector, then I can say A3, A4, A5, A6. So what I can say, the resultant will be what? A1 plus A2 plus A3 plus A4. Okay, A5. We are done. Okay. So sometimes they will ask you that if you know the resultant already, and if you know the first four pass, then you find the fifth pass. The answer is yes. Just subtract the first four from the resultant. You will get the fifth pass. Okay. They may ask you, can you calculate the third pass if you know the 1, 2, 4, 5, you know the first two and the last two pass, you know the resultant, and you're supposed to find the third pass. You can find the pass. That's a Polygon Law. Where else we can see the Polygon Law in our real life? So same is with hockey also, you can correlate, right? Hockey, the same thing happens. They pass the ball using the stick, right? So they ground the shot, which goes from one player to other player. They stop it, they turn it and give a new direction for the pass till it reaches the goal post. Now, in a game of carom, we often deal with this idea of pass. So let me make a nice carom board. Which color carom board you want? If you have any choice, you can let me know. Let me make a dull color carom board, very dull. This is the carom board. Why I'm doing this? Because I want to create a contrast around it. So this carom board is ready. Let me draw some lines to make it nicer. So I'm not a professional manufacturer of the carom board, so you can excuse me for bad design. And now we have the pockets. Yeah, the pockets are very important. Else you can't play it, right? Ah, this pocket is slightly bigger. You can complain to the federation. The caroms are biased. Nevertheless, we can have a makeshift carom board for the demonstration purpose, and then we have to, of course, uh, the queen has to come, else we can't play. So let me bring the queen first. Before that, I'll make a nice. Oh, yeah, that is nice. So you can see there is a queen at the center. You take a striker and you hit the queen. The queen goes, hits the front edge, then side edge, and then many edges. So let's say after hitting the queen, it travels multiple paths. So this is the first hit. Okay. Then after this, it will make a next hit. And let's say, I mean, this is a smart player. Like he knows physics a lot. The reflection property of the carom board. Okay. So how many passes? A vector. So to coin this queen, this may be one of the possible paths. Okay. This could be the possible path. Or if I choose the origin near this queen itself, I mean, of course, I can set up my coordinate system anywhere. Then the resultant vector, we could have directly drawn like this. Correct? So this line, the thin line which I have drawn, is the resultant, is the closing side of polygon. You can see now it completely closes. So now this is the closing side of the polygon, and that's why this is the resultant. So we can say that the R is the resultant of A and B and C. These are literature. A, we are not adding anything. To be very honest, you cannot add symbols. That's meaningless thing. You can only add numbers, right? If I ask you what is the north plus south, it's meaningless. Who can add? North is north, south is south. I cannot add. It's like adding banana with oranges or apple with oranges. Very famous example. Okay. So we are not adding, we are saying that R is the resultant of A and B and C. This is the mathematical literature of saying the same thing. R equals to A plus B plus C, which it doesn't mean we are adding, doing anything. We are just putting into literature. Okay. So polygon law is everywhere, but we are particularly interested in some really nice polygon. What is the nice polygon? The regular one, like which you appreciate a lot. So I know that my polygons are not appreciated a lot in the world, but nevertheless, I have to draw. So you can see the very really bad polygon. Okay. This is a very bad trail. You can see eventually we have to draw it. And we have somewhat better, but can we make it even better? The answer is yes, we can make it even better. So the new trail, the new polygon law is very, very important from the point of view of chapters like wave optics. There is a very difficult chapter in physics called diffraction. So again, there also we need, and to solve some of the challenging problem of vectors, we need to know this direct derivation. Okay. So we will derive from the scratch, and you will see it, and I will request you to also try to derive it. Okay. So in my case, I'll put a name is special polygon. So what is this special polygon? I mean, we have a polygon in which all sides are equal. So every pass, every displacement is equal in value numerically. And the only difference is they change the direction. They change the direction. Okay. So generally, if you're driving a car, let's say you're driving car on a turning. Okay, this is a big road turning, maybe mountain. Of course, I mean, to turn, you will not hit the wall, it will come with this way. Okay, of course, you can't do that. If you hit like this, it's a crash. So what exactly you do? I mean, you don't realize, but anyone who is driving, they tilt the steering slightly left, left, and the wheels will turn slowly, 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 slowly. I mean, it doesn't feel like the wheels are turning, but eventually you make a big turn, isn't it? So if I break down the journey, it looks like something this. I mean, just wait a minute. So you move a bit like this, then like this, slightly you turn, and then you turn a slightly more, and then you turn slightly more again. Every time what you do, you tilt from the previous vector by the same value. I mean, of course, my roads are coming closer. I need to change the road shape. Yeah, that's better. Or this is better. A very curvy road. Okay. Then slightly. So see this driver. What is the driver is doing? He is moving a bit and then slightly tilting the steering towards left. And every time, if you observe, the vectors are turning slightly with no apparent change of size. So lengthwise, I have kept all equal. Okay. The only difference is the angle part. So if you observe even carefully, the angle by which we are tilting the vectors are slightly, and I'm making sure that the tilts are constant every time. It means every vector with respect to the previous vector is turning equally. That's the whole idea. So this is called the really nice. So I will call theta, then again theta, then again theta, and every time. Now compared to the first vector, the second has turned theta. Compared to the second, third has turned theta. Compared to this third, fourth has turned theta. Compared to the fourth, fifth has turned theta, and so on. Really interesting. Now such nice turning is having some application in physics, and therefore we need to study. Now if I draw the polygon law in this particular case, I have this line, correct? This is my polygon law and this is my resultant, like how much I have displaced eventually. So if I know the small displacement, like if you when you walk, your strides are constant, right? When you walk, you have the fixed stride length. Generally you don't stretch too much and shrink too much while walking. Generally we don't, right? So assuming this is like a stride of a person and the person is turning, so he will keep the stride constant, like keeping the vector length constant, and then turning a bit every time. Okay, because you want to go in that way. So this kind of vectors is called the nice polygon. So of course it's not a polygon in exactly the way you think, but what you can see that every vector is having fixed length. Okay, and the angle between two consecutive vectors are constant, equal, right? So in this special discussion, what we can mention here, and I should mention in fact, the length of each vector is constant, and angle between any two consecutive vectors are equal. So the concept is clear, like what we are trying to achieve here. Okay, so the first thing is we have the vector with constant length. So even if you have 10 vectors, all 10 are equal. The second is the angle between any two consecutive vectors turns out to be same value. So that is the beginning point for the derivation. Okay. So how exactly we derive the length? I mean, this is a nice case. You can actually derive it. But how? That's the question. So for that purpose, what we do is we draw a big circle. Okay, this is big enough for derivation. And what we do next is we draw the strides, as I said. First, let me change the color. You can see the strides are almost merging with the circle, right? To make it different, we have to make it bigger. Now it looks like slightly bigger, right? Somewhat the displacement and the circle is part of it. This is the stride number 2. Now I want to repeat this for a very large number. How large? N such strides. And that is why I will just make one as dotted, which means there are many more in between. There are many more in between, which I cannot draw. So what we do, we make a dotted line. This means, so you see 1, 2, and then you see the nth. 1, 2, 3, and then dot, 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 and last n. So how many steps you have taken? N steps while turning. So we have n vectors of equal length, right? And what we are looking for? We are looking for the displacement or the resultant of all such vectors. So this white line is the resultant, correct? And we need to also use the angle part, which let me draw it again. So this angle we call theta. Okay. This angle we call theta. This is also theta. Now we have to use some property of a regular polygon. If we have a regular polygon, we know some property like the relationship between the exterior angle, okay, and the angle that they can create with the center. So if I join with the center, this is a very interesting phenomenon. Just look at this. So let's say the radius of this circle, which I don't know how big is circle, I can call it A, just for the sake of writing. Let's call A as the radius of circle, okay? Not A, small r. So small r is the radius of circle, and the length of each vector is A. Now, given this angle theta, can you guess what will be this angle? Can you guess? Or better, you can derive also. Slightly geometrical work is there. So if this is theta, this is how much?
180 minus
180
theta.
minus theta.
And if that is 181 theta, then this must be equal, right? It looks like symmetrical. If that is 181 theta, then what do you expect this angle? Only 1/2. So what is this angle? Let me change the color and show you. What is this angle? Half of that value. So if I call this angle as alpha, this will be also alpha. Why? Because it's a isosceles triangle. It's a radius, no? So in this triangle, if you look at single triangle, this triangle, the alpha must be same for both, isn't it? So can we say, very careful, can we say, if I want to know this angle beta, 2 alpha plus beta must be equals to 180 degree. Alpha we know is how much? Basically, if this is alpha, this is also alpha. So 2 alpha we know is how much? Pi minus theta. So if we replace, we can say pi minus theta plus beta is pi. Oh, that's nice way of writing. Basically, beta is theta, which means the angle between the vectors is actually the angle subtended by every vector at the center. Luckily, both are same. Geometrically, they are always same. You need to remember this. So beta turns out to be theta. So it means each angle is theta, right? So how many such angles are there? Can you guess how many these angles are there? What is the total angle from here to here? So total angle will be number of strides, number of vectors taken. And we have taken how many vectors? You can see n vectors. So one vector subtend theta angle. So n vector will subtend how much angle in total? Tell me guys, if one vector subtends theta angle, then all the n vectors taken together will subtend how much angle at the center of circle?
N into theta.
Correct. That
Yes,
is
sir.
n into theta. So what we are going to do is we are going to draw it separately, just for the convenience. So now I have the resultant which is unknown, and we have a center. And we have a radius. This is r, this is r, correct? This is n theta, as we discussed. So may I draw the perpendicular? If this is n theta, so the half will be how much? N theta by 2. And the half of this will be how much? R by 2. So can we relate the radius with our resultant and theta angle? Which relation?
Sine.
Very good. What we can write? Sine of n theta upon 2 must be equals to opposite upon hypotenuse. So I got the answer r by 2, or simply 2 will cancel to r equals to r sine n theta by 2. Now what is the problem? The problem is I do not know what is radius. That is my construction. Radius is actually not given. What is given is the length of each vector is a. Can we do something to get rid of r? Can we do something? Yes, we can do something. We can draw the single triangle, the small triangle of length a. Why? Because even for this triangle, the two sides are having same radius r. And this idea we can exploit. So we know this angle is theta. This is r. Can we relate r, theta, and a? Of course, you can do the perpendicular to get the right angle triangle. And now probably you can use it. So this angle is how much? Theta by 2. So can we say that a by 2 is r sine theta by 2? Can we say that?
Yes, sir.
R sine theta 2 is a by 2. You're correct. So, okay, I have missed something here. Oh, my bad. This is 2 will come here. Yeah, we missed the 2 here. Right? R by 2 r. No? So resultant is 2 r sine theta. So now you can see the a turns out to be 2r sine theta by 2. Can we say equation 2? So now we have equation 1 and 2 both having the similar value to r, which is we do not want. We want to get rid of r. So what is the logical step to get rid of r? We can divide. So 1 divided by 2, can we write r upon a as simply sine n theta by 2 upon sine theta by 2? You can check. Is this clear? And now we are done. So we finally got the answer. The resultant is basically a sine this will be your the challenging problem in trigonometry when you study the triangle. I mean, you may come across question like this: finding the length of the side of polygon, and we got it mathematically. So this formula gives you the resultant of n vectors in which every two consecutive vectors are equally inclined to each other, and this we can write as a into the sine n theta by 2 divided by sine theta by 2. So it is having application in mathematics in complex number and at various other places. Now you are not aware of complex number, we can also derive this formula using complex number notation, and that will be the last chapter of, maybe the not last, it will be taught to you at the end of class 12th mathematics, the complex number. And then you will again come across this formula. This is called the summation of trigonometric series. This is called summation of trigonometric series. So we'll come to that. What is that exactly? So R is this much, and now we would like to understand that the path that we drew, like 1, 2, if you turn by equal angle, then it is also possible that you may end up coming to the same place, right? Quite possible. So what about such triangle? I mean, such polygon in which the beginning and the end coincides. So there is no gap to be closed. Now we cannot draw a line to close the gap. So what we can say, the resultant is how much?
Sum of all the vectors.
Which is 0. Because the resultant always gives you the tail of the first to tip of the last, but both are coinciding. So there is no such length, right? We cannot draw anything. Any closed polygon represents what? 0 resultant. So what is the takeaway from here? And you can see clearly all vectors are in the same order. So we do not have the reverse order. Cyclic vectors, these are cyclic. They are in a cycle. So any, what you can write? Any closed polygon in which vectors are cyclic always gives 0 resultant. So what will be the condition in this particular case for 0 resultant? So for 0 resultant, mathematically what we can say, the numerator must be 0. So n theta by 2 must be 0, and when the value of sine is 0, so sine is 0 when angle is 0, correct? Or angle is pi or 2 pi or 3 pi or 4 pi, or so what we can say in general, that this is only possible when this is some integral multiple of pi, where k is some integer. Any integral multiple of pi will give you 0 resultant, which gives you the relation that n theta equals to. So k can be 1. You can say k is 1, 2, 3. So if you add all the angle, and if you see that it is 2 pi or 4 pi or 6 pi or 8 pi, you can say for sure that this will give you 0 resultant. Are you getting the point what I'm trying to convey?
Yes, sir.
So let's say if I give you 3 vectors, and if the vectors having same length, and the angle between any two consecutive vector is 120 degree, what to expect? So 3 vectors into 120, how much? 360, which is exactly 2 pi. If this condition is satisfied, what we can say? There is no question of resultant. This will have 0 resultant because it forms a closed triangle. A, B, C. 120, 120, 120. You can see the angle. So n into theta. N is the number of sides. Theta is, if this is 2k pi, like any multiple of pi, the answer will be 0 because it is going to form the closed polygon. Understood? So let's say if the angle between any two consecutive vectors is 90 degree, how much? 90 degree. And you have 4 such vectors, what do you expect? 90, 90, 90. There is no option, it will form a square, correct? Which means the resultant is going to be 0. Understood?
Yes, sir.
So the idea is simple. Okay. So they will ask you a question like this, that if you have 5 vectors and if the angle between each vector is how much? 105 means 360 by 5, 72 degree, right? So if the angle between any two vector is 72 degree, then 5 into 72 will give you 360.
Yes,
And
sir.
therefore it is definitely a closed polygon, and therefore it will give you the 0 resultant. Because when I say find the resultant, it means you're trying to look for the vector which can join the tail of the first and tip of the second. But if in case they don't exist, you cannot draw such line, which simply means there is no any result, there is no resultant in such scenario. So the R will be 0. Is this clear? Okay. All right. So this is very, very important derivation, and you should derive at least once or twice on your own to get the hang of it. So maybe it may look very weird or difficult, but you have to practice actually on your own. Until you're not deriving these formulas, you will not actually appreciate the mathematics. So please make sure that even after class or during the class, if possible, do derive as I'm deriving. What you really need to remember is the derivation, not the answer. Because answer you're going to forget for sure. After 1 week, 2 week, 3 week, you will forget. Derivation, if once remembered, cannot be forgotten. So you can use it again and again in examination. Okay, so we are done with the various laws to add vectors, and of course, the example which I gave you, the carom or the football, are the actually real life examples. And now we are going to start something called so we'll start a new topic today, that's called position vector. Position vector, right? And how we represent? So we use the R symbol. In various texts, especially the Russian text, if you read any Russian book, they don't use the word position. What they use? A radius vector. Maybe for them, the radius is more intuitive than position. Or anyway, they are Russian, so they will not follow what American will follow. So they have always the conflict with the Americans. You know this from the all the Hollywood movies, right? In every Hollywood movies, American are the survivor, I mean savior of the world. Russians the villain. That's very typical. You can see the phenomenon. And now the Asians are coming into play because we are a big market. So you may see some Indians also working in Hollywood movies. Why? Because they want a bigger audience. Correct? Anyway, so why this vector is important? It's very simple. If I want to ask you where is this point, now the question is irrelevant. Because where is this point is only meaningful with respect to what? Okay. For example, if I ask you where you are, you may say at home, but I didn't ask you from where. So where you are with respect to your neighbor, with respect to your school, with respect to me, with respect to, let's say, King John, or with respect to, let's say, Warren Buffett or maybe Bill Gates. I mean, the question is, this is a meaningless question. Where you are is not a meaningful question until we mention with respect to what, like from where you want to relate or express or represent, you need to mention someone. So position of a, let's say if I ask you where is the star, now you will say which star? No, any star. So you can say anywhere, because that's a nonsense question, must be having the nonsense answer. Where is the star? Like with respect to Mars or Earth, or maybe the world of minions, or maybe Elon Musk. I mean, until we do not mention with respect to what, the question becomes meaningless. So came the logic of position vector, that if you want to specify someone's location, the location must be said by someone. If I am telling your location, then I am someone. And the someone is called observer or origin. In mathematics, we call origin. The origin is someone who will locate you where you are. Okay. And without origin, how you can locate? Okay. So let's say there are two kids playing together. Okay. So okay, I will just do something random. So let's say there are two kids playing in a garden. The kid one and kid two. And the parent of the kids, I mean, is somewhere here. The mama is here watching. Oh no, she's gossiping with her friends. Nevertheless, the kids are playing. That's important. And now you come to the garden and you ask, let's say your mama, like, let's say that let's name the kid. We can name it Bunny and Monte, or whatever you can name it, whatever. So you can name it some random name. You say Bunny and Monte are the two kids, and the mama is, let's say, Nicole or maybe Kidman. Doesn't matter. And you ask Nicole, like, where is Bunny? Now Nicole will point her finger towards the bunny like this. Now you're pointing your finger towards the object. The bunny is the object as described by the mama Nicole. Okay. And then Nicole has no idea where is Monte, because they are playing hide and seek. So you can see Bunny is where, you don't see the Monte. So you go to Bunny. Okay. And then you ask Bunny, where is Monte? The Bunny will point his finger towards this, or her finger. I don't know. I don't describe the gender of the name. I have no idea. So now this is the pointing the finger. Now what? How we can name it? So I can say this is the position vector of Monte as described by Bunny. So we use double subscript notation because I have taken the mama as the origin. So whatever mama will tell, that's the single subscript notation. So now if you ask you where is the Bunny, and if you ask your mama that, okay, if you ask Nicole where is the Monte, she will point her finger like this. So whatever origin represents, we use single subscript notation. But if you try to locate someone or some point with respect to a new point, which is not the origin, you use the double subscript notation. So this is also position vector. This is also position vector. This is also position vector. And all position vectors are represented differently. So the R1, R2 is represented by whom? By the origin. But R21 is represented by whom? Who is presenting that way? R21. Who is
Bunny.
presenting? The Bunny is presenting, correct. Bunny is presenting R21. Okay. So that is the idea of position vector. Position vector is the idea, like how you want to express a position. So to express a position, we need to first imagine an origin. Now, origin can be a person, place, or thing. Oh, it's a noun. Interesting. So origin can be person, place, or a thing. You can take a pole, you can take a road, you can take some landmark, you can call that is origin. That is my point of observation. You can take your rooftop also. Okay. So the position is nothing but the origin. Like if you want to locate something, you need to specify the origin, and then you can draw a line which joins the destination. So let's say if I ask a small kid, where is moon? A really bad question, but okay, you can ask. So you want a good quality moon? Okay, I can do it. So you want Eid moon or full moon? You can choose. I mean, choose it. I have some offer. I can do it. So now this is the moon. Of course, you see the reflecting part as a moon. The shadow is the, of course, moon. Moon is always spherical. It's not in this shape. Okay. You may see a part of it which looks or which gives you the different shape. So it's called the phase of the moon, right? We have multiple phases of the moon. And now if you ask this kid, where is the moon? The kid will point his finger like this. Now, of course, his finger is not big enough to reach the moon, as we know. The kid can point but cannot touch the moon. That's good thing. Else, every kid in the world will pull the moon here and there. That's very dangerous. So it's good. How far is the moon from the earth, by the way, for your mathematical information? It is roughly 384,000 kilometers. Not very far. If you want, you can go. Just consult Elon Musk. I mean, he is offering some trip at some cost, which I am not capable of paying. So I am not going, by the way. If you have any interest, you can directly consult. I have some friends in the Tesla or SpaceX. I can recommend his number. Yes, one of my students is working with SpaceX. Yeah. So now what I'm saying, this origin is the person who will locate object, and we draw a line because we want some mathematical relation. So we want to relate mathematically, we want to put some mathematical number, and therefore we draw some axis, we draw some coordinate, because the coordinate gives you the number line, number system, right? And therefore with this number system you can write the coordinate eventually. So the moon is located in xy plane. If this is the xy plane, I can say the moon is located at some x value and some y value. I don't know how much. If it is in the xyz plane, I mean, if it is 3-dimensional, I can convert into 3-dimension. It's up to me. I will put xyz. Okay. So depending on the dimension, I may need either 2 values for 2-dimension, 3 value for 3-dimension, or 1 value for 1-dimension. I can draw this line as the x-axis. Then I just need only one number to get the location of moon, the x coordinate, right? It is all about how we draw the coordinate system. So in mathematics and physics, when the origin is attached with the coordinate system like x, y, z, what we call as frame of reference. So I'll put as a definition also, what is frame of reference? Let me put somewhere, I have a space. So what we can say, an origin, or you can say a coordinate system, attached to some observer, generally called origin, is called frame of reference. Okay, that is the definition. Yes, you heard it right. Frame of reference has got a definition. And how we define it? Just okay. So how to define the position vector? Simply draw a line joining the point from the origin. And what will be the direction of position vector? Always away from the origin. Okay. Position vector must be away from the observer. Origin means the one who observes. Correct? So that's a simple rule which you need to remember. So note. Okay, let me put a definition. I mean, I have a space, I can use it. Position vector any vector representing a point in space with respect to origin. Understood? And its direction is always taken away from the origin or observer. So that is the definition of position vector. So generally what we do is we draw some coordinate axis. Okay, I can do it here only. and I'm done. And the idea is, if you are dealing with 2-dimension or 3-dimension, accordingly you need the coordinate to represent. So if it is 2-dimension, you can just choose x and y. But if it is 3-dimension, you have to use x, y, and z. That's it. And if it is 1-dimension, then definitely you can choose either x or y or z. So generally, when we practice right now, we are going to practice. We'll start with the 2-dimension because that is most common phenomenon. Like playing carom is 2-dimension, or playing hockey is also mostly 2-dimension. Until you lift the air ball in the air, that's problematic. But still, that is 2-dimension because in air also it moves in a plane, mostly in a vertical plane. Okay. And but if there is a wind and you throw a football in air, it will take a curve path, which is like 3-dimension because we cannot put a vertical plane to confine the football. But most of the questions that we are going to deal with will be 2-dimensional. Most of the problem in physics will be 2-dimensional. So we are at a good position to understand the 2-dimensional world. 3D will be having some questions, but not much. So the question is how to represent position vector. Okay, so to represent the position vector, so first of all, I'll restrict myself to the 2-dimension because that gives you some idea. So let's say I choose a point in a plane. So there is some random point. Now you might have heard about the coordinate. What is coordinate? What is coordinate?
X and Y.
Yeah, but what exactly is x and y? So if we have a point P, and from the point P, let's say you are at point P, if you look towards the x-axis, which number you can see? So if you look towards the x-axis, of course, don't look anywhere, perpendicular. So if you see, you can see this number. And from the same point, if you look towards the y-axis, you can see this number. So this point P represents an ordered pair of number. An ordered pair of number. The first in the order, the first number must be coming from which axis? X axis.
X-axis.
And the second number will come from which axis? Y axis. And you put together in some parenthesis or a small bracket, as you say it. And then you call this as coordinate. So X is the first number, and then Y is the second number. This is called the way to represent the point P. The point P is representing 2 points at the same time. In 3-dimension, how many points it will represent?
3
3
points.
points. One taken from X, other from Y, and other from Z. So this is basically X comma 0. So this point is called 0 comma Y. Then the point P is called X comma Y. Understood? And now this point we can draw from the origin. We can join from the origin. So this yellow line is called position vector of point P with respect to origin. Now because it is with respect to origin, I will not mention origin. I will just say position vector. Because by default it is with respect to origin. If I have to change the observer, I need to explicitly mention. If I have to change the observer, I need to explicitly mention. So if I'm not saying you anything, by default, you will take origin as the point of observation and you will express your answer. Nevertheless, if I call this point as Q, how big is the line OQ lengthwise? So lengthwise, this is X. How big is the line QP?
Y.
The lengthwise Y, correct? So if I draw arrow like this and like this, can we use triangle law? So our R vector will follow the triangle law. So using triangle law, can we say R vector, or basically I can write later on, OP vector is equals to OQ vector plus QP vector, correct? Triangle law. This is a very basic triangle law. And now I can replace by the various symbols. So I can say this is R vector. The OP length is how much? The length of OQ is X. And what is the direction? We know the direction. I cap, if you remember. So when you multiply the length with the direction, it becomes vector. So can we write OQ vector as X I cap? And similarly, can we write QP vector as
YJ cap.
YJ? So what R is saying? R is the vector which is obtained by or obtained from vector OQ and QP. So R is the resultant of OQ and QP vector. And that is exactly the triangle law, the XI cap plus YJ cap. Now, once you draw this, once you write this literature or piece of literature, what is the length of R vector? If you want to know the length, can we use Pythagoras directly?
Yes, sir.
Or square root, under root x square plus.
Correct. So you can write as x square plus y square. Now, of course, we derive using the Pythagoras, but the way we should think is not Pythagoras going into future. So going into future, when you write R equals to xi and yj, okay, anyway, then this is actually equals to under root of coefficient of I cap whole square and coefficient of j cap whole square. What is coefficient? The number which you multiply with I and j. Understood? So what we write here? Okay, I'll put nice way of writing. Oh, no, it was. So the way of thinking is whenever you see something like this, you look for the coefficient. So if, for example, if I write R equals to 3I cap plus 4J cap. So what is the length of R? What is the magnitude of R? Under root of the coefficient of I cap is 3. So 3 square, which is luckily 5. Okay. So if I write R equals to 5I cap plus 12J cap, what is mod of R? So mod of R will be
13.
13. So it's a very famous Pythagoras triplet, right? So you can have some random value also. like no, this is not good. So mod of r is how much now?
Under root 136.
Root 136.
So 136 under. So that's very simple. This is how we can add the modulus. But particularly the magnitude is not very important to us. We look for something more, and what we look for is called direction. So we will talk about direction in detail because that is a difficult concept to digest. So direction means, let's say the x-axis represents east and y represents north. So I would like to know where the guy is heading to. If you follow the path OP, someone walking on the path OP, what is his direction?
Northeast.
So it is not exactly northeast, it is somewhere between, correct? Northeast basically means 45 degree bisector. But it is not necessary, it could be more towards east, less towards north, or vice versa. So what exactly is the direction and how we can express it? So as a convention, we express the direction by writing the angle with respect to the positive direction of x-axis. So the theta is actually representing the direction, which means if you turn by angle theta from the x-axis and if you walk, you will reach the destination. So walk by how much? Let's say if I choose this value. This says that if you turn by theta, which I will calculate later on, and if you walk 5 steps of 5 units, you will reach the point which you are trying to locate. That's the meaning of direction. So what we are trying to do is, if you turn by the some definite angle, and if you walk 5 units, you will reach the destination that you are trying to locate, the point P. From where? Origin. Okay. So how we get this answer, and why theta is only angle we need? Why not this angle? The answer is you can take any angle, but conventionally, what I said, or traditionally, rather it's a tradition. And there is a very famous cliche in literature. Customs after long time becomes rule. Very archaic, but it's very famous. So some tradition which you follow for a very long time, it acts like a rule, isn't it? Like you celebrate your festival in certain way. That's a tradition, right? But now it is like a rule that in that festival you must take a bath, then take a food, or you can't go to play football, come in a muddy t-shirt and enjoy the festival. I mean, of course, you'll be thrown out of the home if mama is restrict. Okay, so the idea is conventionally we have taken the angle as a theta that the direction makes with the x-axis. Okay, and given the angle theta, we can understand how I need to walk, in which direction exactly. So I will show you some direction and the naming convention, which will be good for you. Let me show you. I have some space left here. So let me show you some naming convention and the directional concept. So this we call north, this we call east, then this is south, this is west. So what is this angle? So you can see the angle is with respect to what? East. So this is called theta degree or radian, I don't know what is this. So theta, let's say called degree. Theta degree north of east. So the off will tell you. So what comes after off or of is the angle it is making with. So theta is with which axis? East axis. In which side? In which quadrant? North of it. So it is between north and east. But the theta it is making with the east. Okay. If I take this as the angle, let's call it alpha. You can write as alpha degree east of north. Because now I am expressing the angle with north. So alpha will go with north. Theta will go with east. Is this clear? How we are expressing? So similarly, if I choose something here, let's call this as beta. So what we can say this direction?
Beta degree north of west.
Very good. Beta degree or whatever radian north of west. So of course we are left with only two. You can just finish it, and let's put some 5. So what you can say this direction? 5.
5 degrees south of west.
Correct. South of west. Okay. And the last one, but not the least. So let's choose some other symbol. Which symbol you like? Okay, you can like any symbol. Delta. So how we can express this? Delta.
Delta degree east of south.
Very good. So if we have no biasness, if we have the equal bisector of the angle, like if I am not biased towards north or east, if I exactly bisect the angle at 45 degrees, then what we can say? Northeast, northwest, southwest, southeast. This is 45 degrees. Clear? So when you say northeast, it means you are saying that okay, neither north nor east. It's exactly between. But if it is biased, if it is more towards one than the other, the convention is north of east, east of north, and so on. I hope this convention is clear, not very difficult to understand. So what if what if we don't have the north, south, east, west? We have only theta. I want to just express theta. Then theta must be the angle with respect to positive direction of x-axis. But there's a rule. You cannot write angle more than 180. I cannot write 270 degree from x-axis. That's the wrong way of writing. So there's some unsaid convention, which again I will put it forth here. So direction. First of all, direction is expressed in terms of angle. So direction is expressed in terms of angle. Okay. So conventionally, as I mentioned once again, angle is taken with respect to positive direction of x-axis. All right. So conventionally, angle is taken with respect to positive direction of x-axis. The second point that we should be careful about, theta must not exceed 180 degree. Theta must not exceed 180 degree or pi radian. And third, angle measured in anti-clockwise, which is also called, the American text will use counterclockwise, and the British will use anti-clockwise. Okay. So now we'll use the counterclockwise because British are really bad nowadays. As you know, the PM simply, just quitted, right? So angle measured in anti-clockwise is taken as positive, and the angle measured in clockwise direction is taken as negative. So these are the interpretation which you need to be aware of, like how we interpret the various angle. Okay. So we'll see with the help of some example. No need to worry. I'll show you how to express. In examination, you need to read the answer and to guess which one will match. So angles are generally interpreted. So we'll start with a simple question. Let's say you have a vector, and again I'm saying vector need not to be position, it could be any vector, but we deal with position, that's easy for us. So given x and y coordinate, which one is easier to calculate? Theta is easy to calculate. So which theta, sine, cos or tan? So given x and y, which should I use?
So tan.
Tan. Very good. So the tan theta we can attach
Y by x.
pi by x, right? Now generally you should only take the modulus. Why? Because the sign we can interpret later on by our own logic. So what you get is you get theta as so as a simple rule which I will suggest, always use only the modulus value and then interpret the quadrant simply. So I hope you know the sign convention of quadrant. So quickly let me remind the quadrant thing. So this is called the first quadrant. In the first quadrant, both numbers are positive. So whether you see the x-axis or you see the y-axis, you will see the positive end. Correct? But if you're here on the second quadrant, what you will see? If you look towards the x-axis, you will see the negative x, but positive y. And if you're here, then third quadrant, you will see both negative. And if you're in the positive, fourth quadrant, then
Plus
Positive,
minus.
negative.
positive and negative. So we all are aware of the quadrant and the sign of the numbers. So how to use these ideas to get the direction exactly? So let's take some example. So we have a position vector called R, which is obtained by two separate vectors 3i cap and 4j cap. And this we can simply represent in the first quadrant. Why? Can you see the coefficient of I and j? Are they positive or negative?
Positive.
So
So
positive.
both are positive. So which quadrant they are representing? First.
First.
So we can say for sure that the vector must be lying in the first quadrant. So I am not worried. So I know that I have some point called 3 and 4 in the first quadrant, and then so this is 4, this is 3, this is theta. So you just find the angle. What is tan theta? Luckily, it's a very famous answer.
53.
Now, if we are not lucky, I will just write tan inverse 4 by 3. And by looking at the actual value, I can see clearly that they are positive. So this is the only possible quadrant, right? My answer is actually like this. So the vector is making what angle with the x-axis? 53. Because to go from x-axis to the vector, so if I choose something hypothetical, let's say, let me do it. This is the x-axis. To go from here to the vector, how much I have to turn? I have to turn by
53 degrees.
50 degrees. Correct. So to go from here to here, you have to turn like this. And in which sense you are turning? Clockwise or anti-clockwise? Clockwise.
Anti-clockwise.
Sorry, anti-clockwise. So as per the convention, if we turn anti-clockwise, the answer must be
Positive.
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 So this will be my answer. Okay. So let's take the other scenario. I will choose the same answer. I mean, same question. You can clearly see which quadrant we are talking about now.
Second quadrant.
Second quadrant.
Very good. So you know this is second quadrant because the x is negative, y is positive. So my triangle will be like this, right? I mean, I'm going to do the triangle this way. Lengthwise, this is 4. This is 3. Let's call this angle as alpha. Always choose some value, not theta. So what is tan alpha?
4 by 3.
Alpha is tan inverse. Correct? But how we represent the angle? We take the angle from the positive direction of x-axis. So you have to turn from here to here. So you have two choices to go from x to there. Either go this way or this way. But the rule says we cannot exceed more than 180. So this way is wrong. I cannot go this way. So I'll go again anti-clockwise, right? So from positive x direction, I'll turn anti-clockwise till I match with the direction. So to do so, how much I need to turn is called the angle or the direction of the vector. So the direction is not alpha, it is theta, which is how much? 5 minus
180 minus alpha.
Correct. So you can write a 180 minus alpha, you can write pi minus alpha, and alpha, how much we got value wise? Now, luckily, we know that this represents 53 degree. So theta turns into how much? 127, right? So now you know how to represent direction. Okay. So let's take the third example just to have the clarity. And you know which quadrant we are talking about now? Which quadrant?
Third quadrant.
Third.
So we are not supposed to know the angle from the x-axis in the beginning. You just find the acute angle. You just find the actual value of angle. Then interpret accordingly. So lengthwise, this is again 4. This is again 3. Let's call this as alpha. So we know the alpha is tan inverse 4/3 or 53 degree, right? But the question is, what is the angle? So we have two choices. We can turn anti-clockwise and tilt turn here. But this is wrong because we have to exceed 180. It's like 180 plus alpha. Correct? So if you turn anti-clockwise, you have to write 180 plus alpha. Now, is it exactly wrong? The answer is no. It is simply interpretation, so it is not exactly wrong. Generally, the convention is we write the angle which is less than 180. Now, this direction we can express in two ways. Either write 180 plus alpha, which means you have turned anti-clockwise by the value of 180 plus alpha to match the direction of given vector. Or why not simply move this way? But to move this way, you have changed the direction of rotation, clockwise rotation. So how the reader will come to know that it's clockwise? We change the sign convention. We write minus, which means I have to write this as minus theta. So first I'll find theta, I'll put a minus sign. So what is my theta? So direction is what? Minus pi minus alpha. So you first find the value, which is pi minus alpha. You simply put minus sign. Why? Because I want to convey the message to the reader that dude, I have turned clockwise to get this answer. So you must turn clockwise. So the minus is for interpretation. Of course, I'm not writing minus angle. Angle cannot be negative. But how I'll convey this message to the reader who is reading my text? So we use sign convention. And what I said in the beginning, the anti-clockwise we take as positive and the clockwise rotation we take as negative. I have mentioned somewhere. You can check it out. So my answer is how much? Minus 127 degree. Or if you're not the fan of angle less than 180, you can write plus of 180 plus 53, which is how much? 233, right? 233, correct? Now this is not a wrong interpretation, but generally as a convention, what I said, we choose the angle less than 180 to express. Now, sometime why I need to teach this, because sometimes many textbooks they do not follow convention and they do mention the answer in both ways, this way also. So with the moment you see a negative angle, don't get worried. Angle is positive. Negative is interpretation that turn clockwise to get the direction. And from where you need to turn? From the positive x direction. Is this clear? Anyone having any doubt, please do ask. So I hope there is no doubt in this.
No doubts.
Excellent. So for the sake of completeness, let's take the last example. So you know which quadrant I'm talking about?
Fourth quadrant.
Fourth quadrant.
Correct. So we're talking about the fourth quadrant. And okay, so this is the so we'll just take the value wise. We don't take the angle eventually. So we take the value, and alpha is again okay. We know the answer, tan inverse 4/3 or 53 degree. Luckily we know the answer, so we are mentioning 53. So to get this angle, there are two ways. Either you turn completely like this. Not recommended. Why? It's more than 180. But the easier way is just turn clockwise. So if you turn clockwise, it means you are where? In the fourth quadrant. Correct? So from the positive x-axis, if you turn clockwise, you are in the fourth quadrant, isn't it? And now we can write the answer. The direction is minus alpha. That's it. Do you realize this? Minus alpha. So I can write theta is minus. Just this is the answer. So theta turns out to be minus 53 degree, and this is how we interpret various angles. So next time when you read trigonometry and someone asks you what is cos of minus 30 degree, don't worry. You find cos of 30, but minus means which quadrant? Fourth quadrant. Minus 30 means you have to turn clockwise by 30 degree. So you will lie in which quadrant? Fourth quadrant. And when you learn about the sign convention of the trigonometric ratios in the fourth quadrant, cos is, anyone knows? In the fourth quadrant, the
Cos is positive.
positive.
Hmm.
So you must have the acronym add
So ASTC.
yeah all silver teacup, right? Something like this.
Sir, I remember it as all science teachers are chore.
Oh my god. I'm not. All silver
Except
teacup.
you.
So add sugar to coffee or all silver teacup, or as you say ASTC. You can remember the way, which means the first is called all. All are positive. Any ratio you can take, all are positive. The second quadrant will tell you that the sign and its you can say the opposite, which is cosec, are positive. The third will be tan and cot, because they are inverse of each other. And fourth is cos and sec. So these are positive. So in the first, every angle is positive. And that is why the cos of minus theta is actually cos theta. That's why the rule. But if I write a sine of minus theta, we are in the fourth quadrant in which sine is negative. So we have to write minus sine theta. So tan of minus theta, the answer is the fourth quadrant we can write minus tan theta. But if I write cos of minus theta, no need to
Cos
solve,
theta.
just write cos theta. Why? In the fourth quadrant, cos is always first. So everything else then cos in sec will be negative. And that's how we have the formula in the case of trigonometry. So when I will teach you trigo, I will teach you all these things anyway. It's good to know the convention, that why these conventions came into picture. The angle cannot be negative. So when you see a negative angle, try to understand, you need to interpret. Angles are positive. A negative is it requires some interpretation. And what is interpretation? Turn clockwise from the positive x-axis. Understood? Is this clear? Yes or no?
Yes, sir.
Okay. So this is very, very crucial information. So now we'll see the position vector in 3 dimensions. So 3D requires imagination. And it is almost difficult to produce the 3D effect in a 2-dimensional paper. But I will try my best. So let's say it's a 3-dimension. You can choose the direction of x, y, and z as per your own convenience. So I am choosing this direction as the x-axis. A thinner line will do. This is the y-axis. And now this is the z-axis. Okay. So we have 3 axes, x, y, and z axis, as you can see. And these are mutually perpendicular. Although it doesn't look, but it is actually mutually perpendicular. And if you don't believe me, look at your room. Look at the corners. Are they mutually perpendicular? Yes, they are. If it is not, then your room is mostly not Indian, maybe influenced by some other architecture like European or maybe the Italian. Our rooms are quite perfect. The pigeonholes in India, the construction is mostly pigeonhole construction. We create boxes, okay, because that is easy to replicate. That's the reason. And such constructions are faster to complete. If you choose some random design, then difficult to repeat the pattern. The corners are not perfect, and you need some extra measurement every time. So it's a painful job. So that's why most of the constructions will try to create the square or rectangular shape. And that's logic. Anyway. So now the XYZ axis is shown to you. So if you look at the point P here, you can clearly see it is neither in the x-axis nor y nor z, right? So this is called, it is in 3 dimensions, because from the point P, can you see the y-axis? Yeah, you can see. Can you drop a perpendicular from the P point to the y-axis? And if you want to drop, then how it will look like? This red line is actually perpendicular. Do you realize this? Very difficult, but that's the reality. Now, if I want to drop a perpendicular from the point P to the x-axis, how it will look like? Almost, I mean, I know you won't believe me. This is perpendicular. The green line is perpendicular from point P to the x-axis. Yeah, it doesn't look like, I can understand. It certainly doesn't look. And what about the z-axis? Yes, somewhat you can see this is fine. This is fine. This is my God. Okay, sir, I'll just digest because you're saying. For the time being, yeah, do it. Because these are multiple views and therefore you cannot see all the views correctly. So automatically, when I try to project the world, which is 3D world, into the 2D world, some sort of distortion will take place. That is logical. I mean, it should be. In fact, distortion is there. So maybe I can choose other view to make this possible. How? I'll draw a small one. I will simply shift the orientation. And see, suddenly you can see this side better. So I can see this x is much better than before. The y is as usual. And anyway, z is fine. And where is our point P? And now if I ask you, can you drop a perpendicular from point P to the x-axis? Quite logical. This looks like this. And we should believe that because this is perpendicular, the entire plane is perpendicular to the x-axis, right? Isn't it? So x-axis is normal or perpendicular to the plane itself, isn't it? Which plane? This plane. Oh, you can see this now. So this line is, you can see, is perpendicular to the plane itself. This is also parallel to x-axis, isn't it? So can we say the entire plane is perpendicular to the x-axis? Can we say? So any line which you will draw in the plane will be normal to the x-axis, isn't it? Okay, do one thing. You can see your floor. Okay, drop your pen. Drop your pen on the floor, anywhere. And then you stand up and check, is your direction and the pen is perpendicular, yes or no? Is the pen and you perpendicular if you stand on the floor? And does it matter where the pen is? You can just draw anywhere. You can just throw the pen anywhere and you will see that the direction of pen and your direction is mutually perpendicular. Okay. So this plane contains the diagonal and the x-axis is perpendicular to this plane and so to the diagonal, isn't it? So any line which you will draw in the plane will be at the right angle to the x-axis. Do you realize this? Maybe, yes. So I have just shown you the two perspective. Like you can change the perspective as you wish. So most of these things are depending on the imagination. You have to think of various plane and try to create your visualization. The z axis is actually towards myself, towards me, normal to the blackboard. Okay. So how is the z axis? Normal to the plane, the blackboard, coming towards me out of the plane. Okay. And now if I draw the what? Position vector like this or like this. I don't know which one is better. I think the bottom one is better, right? It gives better picture. Now, how to define the direction of the OP? How to take a theta? So can we take theta from x-axis to guarantee that I can achieve this line? Let's say if I tell you the angle between the OP and the x-axis is 30 degree. Let's say so. The simple question is this information sufficient to track the direction? So knowing the angle with respect to x-axis is sufficient, yes or no? What you believe? If I tell you that 30 degrees, 60 degrees is the angle that the vector is making with x-axis, can you locate the OP vector correctly? You cannot locate, right? Why? Because it's not a two-dimensional question, it's three-dimensional. How many vectors we can draw with the same angle with x-axis? Can you guess? Infinite. Let me show you. Just a minute. So let me draw the axis once again. All right. So imagine a cone. Imagine a cone. Imagine a cone whose axis is the x-axis. And now you will agree with me. What I'm trying to demonstrate here, no matter which slant you choose, all will make same angle with the x-axis. Do you realize this? Because the angle, this angle is called semi-vertical angle of the cone, right? And the theta is for every slant or one particular slant? Tell me. Am I audible? So the question is, okay, maybe you're not still getting the 3D view. Now you can see this better. So do you realize this? The x-axis also represents the axis of the cone. Luckily, and the axis is symmetric with respect to the entire curved surface or slant. So, like any slant you take, the angle from the x-axis will be same or different.
It's the same.
Same.
So, what I'm trying to explain that by giving you theta, can we fix the OP direction? No. Because P can be here, P can be here. I don't know which P I'm talking about. So if you give me only one theta, I cannot tell you the answer. And this leads to the concept that in 3 dimension, one angle cannot determine the direction of a vector. So how many angles we need minimum? How many angles now we need? And the answer is we need 3 separate angles. One with X, one with Y, and one with Z as well. And the triplet of angle will fix the line. Even if you give me 2 angles, you cannot fix it. How? I can draw one more cone. Understood? So again, even if I give you 2 angles, like one alpha and one beta, still we can have multiple slant here. So one beta is not sufficient, right? So we exactly need 3 angles to make sure that the vector is perfectly determined. See the difficulty. The moment you switch from the 3 to 2 to 3 dimension, in 2 dimension, one angle was sufficient. And for the obvious reason why? Because the 2 axes are complementary. So if I give you X axis angle, Y is 90 minus theta. No need to give it separately, right? And so one was sufficient. Now what is problem here? Here alpha is not giving the answer, beta is not giving the answer. I need all 3 angles, alpha, beta, and gamma. And that is why we define something called direction cosines. So we'll study the direction cosines after the vector is represented first. So let's go to the representation part. How to represent R vector? It's very simple. Try to walk from O to P along the edges. You can walk like this. Let's call A. Walk from A to B. So this vector we can define, isn't it? Which vector? The bottom one. So let's call this vector. What is this vector is representing? What is OB vector representing? Can you guess? So from the bottom triangle, using triangle OAB, can we say OB vector is OA plus AB? And you can clearly see OA is XI cap and AB is ZK cap. Do you realize this? And now we are done because I can take OB and QP vector, BP vector. So in triangle OBP, can I say OB vector plus BP vector is OP vector? Okay, we are using triangle of again and again. So we are done. R is how much? What is OB by the way? XI plus ZK. What is BP? BP is parallel to y-axis. And what is the length of BP? Y. You can check. Is this clear, guys? How I am writing? And if I rearrange properly, it's pretty simple. I can write XI plus YJ plus ZK Nothing extraordinary happened. Just we need to write the third term, zk cap. So in 3 dimension, if I give you 3 coordinate, how to convert into vector? Just write first coordinate I cap, second j, and third k cap. That's pretty easy. And also how to find the magnitude?
Root and then squaring all the.
Yeah. So first you find the length of OB. What is the length of OB? Which itself is x square plus y square under root. From the bottom triangle, you can use Pythagoras. So how big is this length? Correct. And of course, so the if you do it, you can get the answer as just square the coefficient of I, j, k and add them. Isn't it simple? Squaring the coefficients and add them. And of course, take the root at the end of this. So I hope this is clear. So now the question is how to find alpha, beta, and gamma. It's not very difficult. Like, tell me which triangle you can see clearly, which right angle triangle is visible to you in the bottom one. Can you tell me?
So can you repeat the question?
Question is, in the given diagram, which triangle you can see clearly as the right angle triangle? I can let me tell you. I can see OPQ triangle, right? I can see ORP triangle. And I can see OPS triangle. Difficult to see OPS, but at least you can see the two. Which two you can see? OQP. So OQP looks like this. Can I draw OP like this? I mean OQP. Just check. OPQ, OQP. Let me show you. OQ, this triangle. This. Can you see this triangle? Anybody not able to see this?
Yes, sir, we can see.
And can you see this triangle, by the way? This is also a right angle triangle. So the next triangle you can see is I'm just putting into a plane actually. And the last triangle is difficult to visualize, but you can visualize. Only you can visualize. Yes, you can visualize if you want. So I will just draw it for the sake of drawing. So we need to first break into 3 separate triangles. Why? Because angle can be defined only for a plane. So I can define angle if I can draw a triangle in a plane. So basically we have 3 separate triangles. And all these triangles are in different plane. Do you realize this? all triangles are part of different planes, not same plane, isn't it? Just check. If you're comfortable, then I'll proceed further. So what is OS? Can you tell me what is OS length? Can you see OS is X? What is the length of OR? Anybody?
So Z.
Very good. And OQ?
Y.
Y. Very good. So now can we find the tan? Tan is not, cos is better. Can we find
Cos.
cos of alpha, beta, and gamma? So what is cos alpha?
Y upon R.
What is cos beta? Cos alpha is x upon r. No? What is cos alpha here? No? Alpha.
Yes, sir. X upon R.
What is cos beta?
Y upon R.
What is cos gamma?
R upon Z to Y, Z
Z
upon R.
upon R.
You can see these are triplet of cosine. That's why if I put all these together, we call DCs. Or you can write as is this clear? Now the question is, sir, do we need to do this rigorous work to get the direction cosines? The answer is no. You do not need this much effort to get the direction cosines. So the obvious question is there any simple way? The answer is yes. So you must be thinking, what is that way? Let me show you. So the question is how to find direction cosines for any given vector. Answer: find its unit vector, and you're done. So what is R vector? Xi plus yj plus zk. What is R cap? The definition says divide the vector by its magnitude. So once you do so, what you get? X by R I cap, y by R j cap, and z by R. So the coefficient of I cap represents what? Cos alpha. Coefficient of j cap represents cos beta. And the coefficient of k cap represents, and we're done. Okay. So what we realize from here? We realize something. What is that? That a unit vector only represents direction, which can be expressed as this. So what will be the modulus of this vector? So we have just learned how to write the modulus. Square the coefficients and add. So tell me guys, what should I write?
Cos square alpha plus cos square beta plus cos square R.
Gamma. This is gamma. But by definition of a unit vector, what do we know? The modulus of unit vector is how much? 1. So the LHS can be replaced by 1, isn't it? And if we square both sides, what we can get? The sum of square of direction cosine always add up to 1. That's a very famous question generally asked in the examination. If you add the square of direction cosines of any vector, it will always add up to 1, because these things we use for direction. So it should not affect the magnitude anyway. And from here we can derive another relation. And what is that? We can write it as 1 minus sine square alpha, 1 minus sine square beta, 1 minus, and if you look carefully, 3 minus so sine square alpha plus sine square beta plus sine square gamma is equals to how much? 2. Is this clear?
Yes, sir.
So these are the very famous relationship, and I will talk more about this one, the cos square alpha. So imagine there is a room in a shape of a cube. What I'm saying? There is a room in a shape of a cube. Just try to imagine what I'm trying to say. In that room, the biggest line is the biggest line you can draw in a cube is
Diagonal.
the diagonal. Do you realize that diagonals will be equally inclined to all 3 axes? Because it's a symmetrical room. So in a cube, the diagonal must be equally inclined to x and y and z. That I hope you can get the idea that it should be. So the question is, what will be that angle that the edge of a cube will make with the diagonal? So question is, what is the question? Given a cube, so in a cube, oh, that's too small. Now from any angle, this doesn't look like a question of vector, but you can solve using vector. So if we have a cube, then it is natural that every body diagonal will make same angle with all 3 edges. So I can choose this as x, y, z. No? Then I can say if this angle is theta, this is also theta. It doesn't look, so don't worry, because it's like the distorted view. All angles are same for the obvious reason, because it says symmetric, symmetric diagram. So how to find the theta? That's the question. So you can use the relationship that the square of the direction cosine is always equals to 1. And if you solve, you can get the answer. What is the answer? Tell me. What is the answer?
Sir, 1.
Yeah. So what is the answer? One we cannot answer.
So is the answer cos inverse root 1/3?
Correct. That's the right answer. So all got the answer. So what we can write? Cos square theta plus cos square theta plus cos square theta, because all are same, must be equal to 1. So 3 cos square theta is 1. So cos square theta is 1/3. So cos theta turns out to be 1/√3. So theta you can write as cos inverse, and of course it's not 45-degree, right? It is certainly not 45-degree, isn't it? So similarly, if you go to the 3-dimensional, we have the tetrahedron in which we have a separate angle. Of course, our syllabus is not about tetrahedron. You may study in 3 dimension in mathematics. So there is a chapter in maths called vectors and 3D. In 3D, you may have the idea. You will get the idea. All right. So now with this, okay, let's do some practice and then we can stop today's lecture. The next lecture I will start something called resolution of vectors, in which we study how to convert vectors into components, and then we'll also learn why it is important to do so. And the simple answer will be we can add only numbers, not the direction, right? So until they are not in the same direction, we cannot add them numerically. So that's why we'll learn about the components. So I have shared some sheets. You can have you started solving the questions?
Yes, sir, I started.
How many you solved so far? So Shreya and Prashansa, have you started solving questions?
So I started the first sheet, but I didn't have time because my college ends very late.
But anyway, time is something that that's of course it's luxury, but you have to find some time. At least dedicate 1 hour to solving, else there is no benefit. No?
Yes, sir. I'll do it this weekend.
Yeah, please. Because going further, we will have more and more practice, more homework. Okay. So anyway, you have to dedicate your time for this. All right, guys. Bye and take care. And we'll see you on Monday. No, Wednesday. Yeah. So I will share some extra content if I get it. But you can start practicing. You will have some question to solve now. Good night. Take care.
Bye, sir. Thank you, sir.
Thank you, sir.
Bye,
Bye.
sir. Thank you, sir.